Okay, we have chapter 4.3, indeterminate forms. I will try to do this part in two particular cases, in two forms. The first part will be some basic facts, and the second part in the second part we will solve some problems. So indeterminate forms are related to the limits of the form 0 over 0 and infinity over infinity. Of course, there are also particular cases, but we will try to first write the limits in this form, and if we have these two forms, we will use L'Hopital or L'Hospital rule. Let me first give the definition for L'Hopital rule. We have, if we are given two functions, L'Hospital rule. So let's say suppose that f and g are two functions which are differentiable, and moreover with g prime x is not equal to 0 near the point A. So A here is a point. And suppose also that limit in two different forms, limit x to the a f of x equal to 0, limit x to the a g of x equal to 0, or so either these two limits, or limit x to the a f of x equal to plus or minus infinity, limit x to the a g of x equal to plus or minus infinity. So either of them, if satisfied, either the first two conditions or the second two conditions, then we say then limit x to the a f of x over g of x is equal to, so here we have L'Hopital rule, is equal to limit x to the a f prime x over g prime x, f prime x over g prime x. So the main fact here is, when you take limit, you do not apply the quotient rule. You take the derivative. Sorry, the derivative of f prime and g prime are particularly evaluated, and you write directly in the limit. So it means the limit of f of x over g of x is the same as limit of f prime x over g prime x. So let us continue. We have the following. If you consider the following note, in that note we can say that x to the a can be replaced by x to the a from right side, x to the a from left side, x to the infinity, or x to the minus infinity. In other words, all of these cases are true. If you have limit instead of x to the a, you can have x to the infinity. So you can write, instead of a, you can write infinity or minus infinity, or from right side or left side. Okay, we have a simple example. Let us do the following. Limit x to the 0 tangent x plus tangent x over sine x. So let us evaluate this limit. But first of all, when you have this type of limits, you put 0, and you see that what is the history, what can we apply. So when you put 0, we have 0 plus tangent 0 is 0, so you will have 0 in the numerator, and sine 0 is 0 again, so you have again 0 in the denominator, and you say that this is of 0 over 0 form. In other words, you have right to apply L'Hopital rule. So then you say, by LH, let's say, let us use abbreviation LH. By LH, you can have the following. This limit x to the 0, x plus tangent x over sine x is the same as limit x to the 0, derivative of numerator. So you take derivative of x plus tangent x, not the quotient rule. Pay attention. We have 1 plus, so tangent x, if you differentiate it, we have secant square x over sine x, derivative of sine x is cosine x. So now at that stage you can put x is 0. If you put x is 0, we have 1 plus secant 0. Secant 0 is 1 over cosine 0, which is 1. So then we have 1 plus 1 over cosine 0, which is again 1. So the result is 2. So as you see, we have indeed, if you do not use L'Hopital rule, this is a complicated limit, but by using L'Hopital rule, the life is easier. Another example, let us have an example of infinity case. We have ln of ln x over x. Okay, in this question, if you put x is infinity, you have ln infinity, which is infinity in the numerator. Again, ln infinity, infinity of ln infinity. So one more time infinity, we have ln infinity. It is again infinity, and x is infinity. So we have infinity over infinity form. Again, we have right to apply L'Hopital rule. So let's say if we apply L'Hopital rule, sorry, in the following page, let's say apply LH, then we have limit x to infinity. Let me apply directly. So the derivative of the about term, ln of ln x, derivative of inside term 1 over x over ln x itself over, this is the about term, and below term derivative of x is 1, just 1. Then let me rewrite this limit in the next stage. We have 1 over x over ln x, which means 1 over x times ln x. And in that case, as you see, we have here this will approaching to infinity, this will approaching to infinity, infinity times infinity, we have again infinity. So this multiplication will tend to infinity again. Then we have 1 over infinity, which is equal to 0. And really it is not difficult when you apply L'Hopital rule for this type of limits. Okay, next subsection is indeterminate product. Indeterminate product. So in this case, we will apply L'Hopital rule, but you have to use some trick in order to use L'Hopital rule. Again, we have a simple introduction. Suppose that limit of x to the a f of x equal to 0. This is given, and limit of x of a g of x equal to infinity or minus infinity. Either of them is satisfied. Then limit of x to a f of x times g of x. So let me say this is in parentheses. In fact, we have a multiplication here. What is the form of this limit? We have 0 times infinity is of the form 0 times infinity or 0 times minus infinity. So in that case, L'Hopital rule, we cannot directly use L'Hopital rule because it is not of the form 0 over 0 or infinity over infinity. Okay, let me say we cannot apply LH in that form. So in order to use L'Hopital rule, we have the following arrangement. What can we do? If we rewrite f times g as in the following form. So we have f times g can be written as f over 1 over g or g over 1 over f. It is again, so let me say, or let me erase, or it is better to say, no, sorry, okay, or this is equal to g times f. Okay, or better to use in this form. So then what do we have? So the first one will be of the form, this is of the form, what f will be 0 and g 1 over g was infinity, 1 over infinity 0, so this is of the form 0 over 0. And in that form, g was infinity, f was 0, 1 over 0 infinity, so this is infinity over infinity form. And then in both cases, we can now apply LH for those forms, for both forms in fact. Okay, let's see it in a simple example. Sorry. Right example here. Limit x to the 0 right hand side sine x times ln x. This is a multiplication, of course. When you look at this limit, you see that sine x is 0, and remember the graph of ln x. Let me sketch it here simply in a simple form. So ln, this is y is equal to ln x 0 1, and whenever it is approaching 0 from right hand side here, so ln x, whenever x approaching to 0 from right hand side, ln x will be approaching to 0 minus infinity. Okay, obviously from the graph. So then this limit will be 0 times minus infinity form, and L'Hopital does not work for that case. So let us rewrite it as limit x to the 0 from right side ln x over 1 over sine x. Okay, what do we get? Of course you can use the other one too. So this is just one form, so you can also use sine x over 1 over ln x. Okay, both are equivalent. So in that case we get minus infinity over, so 1 over sine 1 over 0, so infinity form. Okay, so then limit, then we can apply let's say apply LH. If we apply LH, we have limit x to 0 from right hand side, derivative of ln x, which is 1 over x over, okay, we have now separately we take derivatives, 1 over sine x minus cosine x over sine square x. You can evaluate it easy. Okay, you can just do in 1 or 2 steps. Limit x to the 0 from right side. Let us arrange the term. Sine square will be above. We have sine square x over x times, with a minus sign at the beginning, cosine x. So as you see here, we have let us arrange the term. We can rewrite this limit as, you know already, sine x over x, so that's why we may have some simple simplification. Sine x over x times sine x over cosine x. I think we can do that. Okay, we can do that. So sine x over x, whenever x approaching to 0 from right side, this is in fact, as you see, sine x over x is 0 over 0 form, and applying one step of L'Hopital give us directly cosine x over 1, and it is 1. But you already know this limit from the previous lecture, that this is a spatial limit, this approaching to 1. And then sine x will approaching to 0, cosine x will approaching to 1. So then we have 1 times 0, 0 over 1, so the result is 1. Okay, not difficult. I'm sorry, the result is 0. Okay, 0 times 1 is 0. And maybe since it is the time to write the following simple limit, you can directly say that limit x to the 0 sine x over x. This is not an example, this is just to remind you. You know this rule already, this is 1, but where does it come from? So okay, we have a proof in fact for that one, but by L'Hopital rule it is easier because we have 0 over 0 form. So it means when you apply LH, we get limit x to the 0 cosine x over 1, and this is cosine 0, and this is 1. So whenever you do not remember this rule, when you confuse x to 0 and x to infinity, or sine 1 over x or 1 over x, so on, this type of questions, most of the students they confuse it with Squeeze theorem when the form is complicated. You can use L'Hopital rule if you have 0 over 0 form or infinity over infinity form. Okay, another example. Limit x to infinity minus infinity x square e power x. So in that case, again we have, if you put minus infinity, so you have e power minus infinity will be equivalent to, let's say, equivalent to 1 over e power infinity. So this is again equivalent to 1 over infinity. Okay, as you see, this will approaching to 0, and this is approaching to infinity. So we have 0 times infinity form. Again, it doesn't make sense for us. You have to change it to 0 over 0 or infinity over infinity form. So rewrite the limit as, rewrite it as limit x to minus infinity x squared over 1 over, or e power minus x, maybe it's better to say in this form. So then what do we have? So this form is infinity over infinity form, okay, obviously, because you have, whenever you put infinity, the above term is infinity, so 1 over e power x will be 1 over infinity, 1 over infinity, which is again 1 over 0, so then we have infinity. Okay, then we can apply L'Hopital, LH, limit minus infinity, so the above term derivative is 2x, the below term derivative is minus e power minus x. As you see, what do we have? We have, if you put minus infinity, we have the above term is minus infinity, the below term is e power minus minus plus e power infinity, so this is infinity with a minus sign. So again we have infinity over infinity form. It means we can apply one more time L'Hopital. So you have right, whenever you have several form, if you after some evaluation, if you still have 0 over 0 or infinity over infinity form, you can apply one more or two or twice or more than twice times L'Hopital rule. So if you apply again, you have 2x, derivative of 2x is 2, derivative of next term is, the below term is minus minus plus, or e power minus x. So now if you put minus infinity, we have 2 over minus minus plus e power infinity, infinity 2 over infinity, which is 0. Okay, this is not again a difficult question, it was easy. Okay, we have now indeterminate differences, let's say. What does it mean? You are dealing with infinity minus infinity form. And let me say, suppose limit of x to the a f of x is infinity, limit of x to the a g of x is again infinity, then limit x to the a f of x minus g of x, so obviously this will be of the form infinity minus infinity. And you cannot say anything about infinity minus infinity because both are not numbers, so the difference is not equal to 0. Pay attention, a common mistake, maybe some of you may do it, but it is not true. Infinity plus infinity is infinity, infinity times infinity is infinity, but infinity minus infinity is not 0. Okay, this is because you can consider two huge numbers, difference of them may be not 0, okay, because they are not numbers. So we have, whenever we have this form, we can rewrite. Again, L'Hopital is not applicable. LH is not applicable for that case. But in order to LH to be applicable, we can rewrite it as a quotient. What does it mean? Quotient means we have something like hx over kx. Okay, how can we do that? Indeed, before L'Hopital, you have already studied this limit case at the beginning of the semester. Let us do it in one example. Limit x to the point 1, 1 over ln x minus 1 over x minus 1. What is that limit? So if you put ln 1 is 0, 1 is 0 is infinity. We have infinity minus. If you put 1, we have 1 minus 1, 0. We have again infinity, so this means we have infinity minus infinity 4. Okay, rewrite it. Rewrite it as. What can we do? We can, of course, make equal the denominators. So x minus 1 minus ln x over x minus 1 times ln x. Okay, so what is the form of this? We have 1 minus 1 0, ln 1 is 0, so we have 0 over 1 minus 1 0, again ln 1 is 0 0, or 0 over 0 form. So you see that we get a L'Hopital form, which makes sense for us. Then apply L'Hopital, LH, limit x to the 1. So now you take the numerator and denominator limits separately. 1 minus 0 minus 1 over x over, so derivative of first one is 1 times ln x, so this is ln x. Derivative of second one times first one, x minus 1 over x. Okay, obviously. If I rewrite it, let me see it again, x to the 1. 1 minus 1 over x over, and here we have ln x plus x minus 1 over x. If you make this as, if you make the denominator equal, we have x minus 1 over x, and here if you again rewrite that one, you have x times ln x plus x minus 1 over x, and these x's in the denominator, they cancel each other. In the next step I will have limit x to the 1 x minus 1 over x ln x plus x minus 1. But if you write again 1, we have 0 above and 0 below, so this is 0 over 0 form. One more time, and apply again L'Hopital. Okay, if we apply again L'Hopital, what do we have? Limit x to the 1, what do we have? X minus 1 derivative is 1 over the below term, derivative of x is 1 times ln x plus derivative second one times first 1 over x times x, we have 1 plus again derivative of x is 1. So now if you put 1, we have 1 over ln 1 plus 1 plus 1, which is ln 1 is 0, so we have 1 over 2. So you see, as we have a simple way to evaluate infinity minus infinity form limits. So next one is indeterminate powers. So here you will have 0 power 0 form, infinity power 0 form, and 1 power infinity forms, let's say. So in this, the first one, you know already, this is not undefined, 0 power 0. Infinity power 0 is also undefined, but some of you may confuse the last one. 1 power infinity, this is not equal to 1, because infinity is not a number. Okay, we do not know at which power we have, because infinity is not a number, so it is undeterminate form. And the limit will be of the following form: limit x to the a f of x power g of x. So here then you get one of these. So either f goes to 0, g goes to 0, or f goes to infinity with g tends to 0. Then the last one, f tends to 1 and g is tending to infinity. So here we have a note. Okay, if we have these types of limit, note, if y is equal to f of x power g of x, then you can indeed use the following: take ln of both sides, ln y equal to g of x times ln f of x, and then or you can say, or f of x power g of x can also be written as e power g of x times ln f of x. Okay, both are, so either you use that one, so both are true. Use one of them. Use one of this. One of them. So let me see it in an example. Sorry. Example. If we evaluate limit x to the 0 cosine 3x power 5 over x. Okay, what is the form of this limit? Whenever cosine x tends to 0, we have 1. 1 power 1 over 5 over 0, we have infinity. 1 power infinity form. Okay, L'Hopital doesn't work. Okay, we have no L'Hopital. LH cannot be applied. But if we arrange the term, so okay, rewrite it by the following. So let y to be cosine x power 5 over x, as we stated above. So you are free to use one of them. So ln y will be 5 over x times ln cosine x. Okay, oh, indeed we have ln of cosine x power 5 over x. 5 over x is a power, so we can write it at the beginning. Then take the limit, take limit of both sides. By that limit we get what? We get limit of x to the 0 ln y will be equal to limit of x to the 0 5 over x ln cosine x. We have cosine x or cosine 3x? Maybe I confused here. Cosine 3x. Sorry, cosine 3x. All of them are cosine 3x's. Here also cosine 3x. Okay. Now if you look at this limit, if you consider the above term as that one, so this is one term, this is the other term, numerator and denominator. Whenever x tends to 0, we have cosine 0 is 1, ln 1 is 0, this is 0, and this is again 0, so this is of the form 0 over 0. Then I am ready to apply, so you have now right to use L'Hopital rule. Apply LH. So we get the following: limit x to the 0 5 times, so derivative of cosine is minus 3 times sine 3x over itself, cosine 3x over 1. Derivative of x is 1. So if I rewrite it again, x to 0 minus 15 times sine 3x over cosine 3x. Since we have sine 3x, whenever x tends to 0 is 0, this will be 0, but this is 1, so then the result is 0. Okay, this is not a complicated limit, but you have to do some examples. Maybe we can, okay, we can stop at that point, and let's say examples in the second part. So let's say examples for the whole of the L'Hopital rule. So I will do it in the next part. So let us stop for a break, okay, for some minutes.